Don't cry, Abu. Don't cry. Abu Bakr al-Baghdadi. Al-Baghdadi. Okay, so we are, let's check, let's do a mic check. Mic check. Mic check. 1, 2, 3, mic check. 1, 2, 3, mic check. We have a good mic. Very good mic. Let's check messages. I don't see any YouTube messages. Everything's fine. Oh my god. Okay. So this is the ticking wave has reached the tick detector. This is the tick detector. So this is the ticking wave transmitter. This is the transmission initiation. The ticking, it's not a ticking wave, it is ticking wave transmission initiation. Okay, so tick, and then it hits home. It got to the other side. So it's going to be detected. This is going to be figure 6. Figure 6. So this is the talking wave. This is a transmission initiation. This is the transmission initiation of the talk. So we're going to destroy this wave. We can't. We cannot, even though they are. How do you delete? There's no way to delete them? You have to delete them one by one. Okay. Abu Bakr al-Baghdadi. Don't cry, Abu. Don't cry. Okay, so we're gonna take this guy and just move it to here. This is the transmission initiation, but what I'd like to do is take all of this without this and without that and move this to the top. So this is the transmission initiation of the response. The talking is the response. Just, I want to make sure they know that this is talking. The ticking and the talking. So it's a tick-tock. 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 Tiki-toki. 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 All right. So the talking response wave transmission initiation. Okay. And the same goes, we need to do the same on the way back. So copy. This is going to be 7. 7. This is going to be the talking wave has reached the tick, well, the talk detector. So the talking wave has reached the talk detector. So we need the talking, add to personal, talk, add to personal, tick. So we're going to copy this like this. Like this. Like this. Like that. Boom. So the talking wave has reached the talk detector. Okay, so that is a tick-tock cycle. So we're going to restart the second. This is the first ticking cycle. The first. This is going to be figure 4 is the first. Now we're going to do, I'm just going to copy this and I'll say, okay, this is going to be the second ticking cycle. This is going to be figure 8. This is going to be the second ticking cycle. Transmission initiation. Transmission initiation. So this is going to be the second ticking. So we remove all of these, except for the inner one. Take the inner one and bring it all the way up for the second ticking cycle transmission. Okay, that's pretty clear, I hope. I mean, I'm talking to people who are geniuses, so this is the second ticking cycle. Okay. So what I need to say now is the distance is constant and the tick tock is a constant. This is the measurement of time. This is time. Now, in reality, it could be that it's moving, but it doesn't make a difference. So we can go back to this guy and we can say, okay, let's assume it's moving. It's still, as far as the duck is concerned, the clock is always going to be tick-tocking. It doesn't matter what the speed is. So it's always going to be distance over time. The distance is constant as far as the duck is concerned, obviously. And the time is the tick-tocking as far as the duck is concerned. So it's always going to be the same distance over the same time. So it's always going to be a constant speed. So the talk, Okay, that's just the mechanism. Okay, the next step is, let's assuming motion. So you could argue, okay, that was a stationary, but let's see what happens when it's moving. So this is going to be a moving, thinking maybe instead of a linear progression of the numbers, of the numerals, maybe we should do, that was 1.1, 1.2, and this is going to be 2 point. So this is going to be 2.1, because this way we can add more in between. So 2.1, this is going to be a, so this is going to be a moving, this is going to be, now we're going to say that it's, we know that it's moving. A moving rubber ducky. This is going to be a moving rubber ducky. Let's assume that it's moving. We need an arrow. I think these are the arrows. Okay. This is the velocity. So we can just write velocity. This is the velocity. It's a moving rubber ducky at velocity, at some velocity. Zzz, it's a moving rubber ducky. Wait, why is the border pink? All the borders are pink? When did this happen? That's weird. Okay. So this is 2.1. So let's correct all these to be, this is 1.1. 1.1. We have a message. 1 second. So this is 1.1. This is 1.2. So we need to just copy the 1 point. There's somebody in Discord. What's going on? Your stream stopped working. Really? What do you mean? When? Are you watching my which one? Oh, I took it offline. You mean the previous one? I had some personal info by mistake. It is just doing diagrams. Okay. Wait, did I? Oh, I didn't do the thing. Let me just copy this and add it. Okay. Here's the link. Let me read a message. Mhm. Okay. So all right, let's continue. So this is going to be 1, 1.3, and this is going to be 1.4. 1.5, 1.6, 1.7, 1.8. Okay, so that's the one series. The two series is going to be a moving rubber ducky at some velocity. At some velocity relative to at some velocity um relative to the water. So this is going to be the velocity. Maybe I'll put it here. The velocity is some velocity. The rubber ducky is moving at some velocity relative to the water. Moving rubber ducky at some velocity. This is the velocity relative to the water. So this is now the rubber ducky, and we don't need the signal yet. So it's moving. Velocity of the rubber ducky relative to the water. Okay, that's 2.1. 2.2, it's going to send a signal that's going to go sideways. So 2.1, 2.2, 2.2. Let me just respond. So this is going to be 2.2. Tick, ticking wave initiated. Ticking wave initiated while in while experience while moving while moving. Okay. So this time, maybe what I can do is, I wish I could select things but not others, but it's impossible. So maybe we should move it here. It could be in the center. The problem is the waves are going to. I don't think the waves are going to be such an issue, are they? Anyway, so it's going to be like this, but maybe I should say. Oh, the wrong thing is growing. So what I want to do is. No, it doesn't make any sense. No. Okay. Um, so we need this, but without the arrow. Or maybe I'll leave the arrow over here, a smaller arrow. Just don't forget that we're still moving to the right. We're in transition. Okay. Ticking wave initiated. So we need the ticking wave to be initiated. I need to copy the ticking wave, or we need the ticking wave from before. So let's go take the ticking wave, this guy, copy, and we're at 2.2, and paste. Okay. Ticking wave initiated while moving. Okay. This time the waves are gonna move to the side. So this is going to be 2.3. Ticking wave, ticking wave reaches detector while moving. So it's going to be diagonally. It's going to take much more time. This is the way Einstein should have explained it in his original paper. I don't know how. I need to see how he wrote it, but we need to have a discussion about waves. So I don't know what Einstein did. Oh my God, why is the water so distasteful? What happened? What's going on? This is weird. Terrible. Really strange. The water was so delicious, and now it's so disgusting. Disgusting. Uh, Very nice. Let me see, everything is good. We need to charge this guy. Very nice. Okay. So this is the ticking wave reaches detector while moving. So we need to copy paste and increment the size like this. But now we need to move maybe one to the left and one down. And copy paste. Magnify appropriately. One to the left, one down. Copy paste. Magnify appropriately. One to the left, one down. So you can see that it had to go beyond by a little bit in order to reach the detector. We never mentioned that the detector is at the center. We need to mention that the detector is right opposite That's the location of the, because otherwise it's going to be confusing. They're going to say, wait, it could have reached before. What are you talking about? But what's interesting is that we're getting one, two, three, four, but that doesn't mean anything. The point is that the speed of the wave, we agree, is a constant. We know that the speed of the wave is a constant. So we need to mention it. The speed of the wave is obviously a constant. This is water. Water waves. The speed of waves in water is a constant. So we need to mention these two things. So mention the speed of the waves is a constant. We know this as the, you know, or that's a given. Given the speed of the water surface waves is a some constant. Given the detector is at the center of, if it's at the center, then we need to make it smaller. We can't have it so big. It's going to be confusing. Center of the rubber ducky. So make it, it needs to be tiny. It can't be so big. It's going to be confusing. Make it, make it smaller. La la la, la na na na, li la la, la 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 la. All right. All right. Oh, 4 people are watching and not committing suicide? How is that possible? Okay. So the ticking, oh, my ear, my ear. Okay. The ticking, oh, oh my God. Okay. Okay. The ticking wave reaches the detector. So, right. So obviously, this must have taken a longer time for us. This is time dilation. So we see the time dilation, obviously, but the rubber ducky cannot tell that it's moving. There's no way. It could use an interferometer. So notice that the rubber ducky could use an interferometer to know that it is moving. That should be a note. Notice that the rubber ducky could use an interferometer to detect that it is moving. Okay. So the ticking wave reaches detector while moving. What are we trying to say? What are we trying to say? trying to say that this is time dilation. Right? It's moving to the right, but the wave has inertia, so called. The wave, no, it doesn't have inertia. The wave, yeah, the wave has, you could say, inertia. The wave is waving based on wave mechanics. The wave doesn't care about the rubber ducky. So the wave, as far as the wave is concerned, the wave went directly, it expanded. As far as the wave is concerned, it expanded normally. But the rubber ducky moved. We should show that. We shouldn't show it like that. This doesn't make any sense because I want to say there's only just one wave. A tick is a wave. It's not multiple waves. So I need to show that the wave, yeah, the wave moved downwards. The wave expanded normally. The wave should have expanded just like before. But the rubber ducky has moved. So we need many more waves. Right, so we should take, we can't, or can we? So we should take this rubber ducky without this, without that. So take this rubber ducky. This is a misconception. We don't want this. So instead of this, I'm going to remove this, remove that, remove that, place this. So let's take this rubber ducky. Nope. Yeah, it needs to be here. So this arrow needs to be on top. Bring to front and bring it here. So the rubber ducky is moving. So in the previous slide, this was here. In this slide, in the previous slide, it's moving. So now this without that needs to move. Say it needs to move. Well, I can't go too far. This should be enough. Now, in all the images, we need to make the detectors small like this. And even the rubber ducky should be smaller. There's no point in a big rubber ducky. Anyway, so we'll take this wave, and the wave has to keep expanding, but it's going to run off the image at the top. So we need to move, maybe make it a little bigger or something, but we need to move it like this. We'll see. We're running out of space. So I'll just magnify. I need this to be bigger, at least for now. Okay. So we'll take all of this without this, and we'll just put it here. Okay. Now we'll add more. The wave is continuing, and even one more. No, 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 no. We need to copy paste one more, basically like this. So now the wave is detected. Let's say before it missed it. Is this is is it straight or is it's crooked? Oh my god, the green lines are crooked. They're not straight. Jesus Christ. I shouldn't use a line. Never use a line because a line could be offset. We need to use a rectangle. So we need to go back to all the images and fix the detector. This is so much work. There it is. We need to put two square detectors. So one is going to have to be here and make it a little like a 4 pixel. Make it green, but you got to put it behind. Order center back. So this, oh my god, what a mess. So we need to undo. Order send backwards. Order send backward. Impossible. Oh my god. Oh my god. What a nightmare. What a nightmare. How do you do that? How do you send it? So basically, we need to keep the original, but convert it. Can we convert this? Change shape to a square. What? What did we just do? What is going on? 1 second. What is this? What did we change? Yeah, we selected the wrong guy. So tab, 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 this one. So we can't, okay, no problem. So we need to right click it without the mouse. So we have the menu, and this is going to be change connector. Oh, it's a connector. So you cannot change it to a shape. Impossible. So it was not a good idea to have a connector there. It doesn't make any sense for this to be a connector. It needed to be something completely different. Yeah, we gotta get rid of them. And these have to be, yeah. But how do we do it? I think it needs to be combined with this guy. Okay, so let's move this off. Let's take all of these guys without this. Nope. Take, oops. So remove this. So take these guys without this. Oh, I can't. I cannot take, it's selecting these guys, but I don't want to oh, once I'm hitting escape instead of control. Okay, so now we're getting these guys. These guys, they need to be at the front. So they're going to be bring to the front. This guy, yeah, the problem is that there's this has blue water, so maybe we need to remove the background so that everything can be seen through. Yeah, that would simplify everything. Let's just make this transparent. How do you make it transparent? So you just select this. Everything should be transparent. That will simplify the work. La 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 la. So now, yeah, and the detector is just going to be a square or something like that. So the detector, I would even, the detector would have to be something like this, but we made it bright green like this. Okay, so we need another one. It's going to be at the bottom like this. Okay. Now the question is, can we, this should always be together. This and this and this should be one thing. Group. Now it's a group. Okay. So now no, they're not a group. Wait, this and this. Ungroup. So it is a group. This align center. What do you mean? So it's a group? So yeah. Oh, okay. So now, so this started off here. And now it's just gonna, and can I group these together? So now this thing is gonna move to here. Let's do Control Z. Right, so it was here. Now it's just gonna move. Even this is good. Yeah, this is good. So it moved. Maybe we should show both the original position where it started and the new position. So the original will make gray. Oh, that's the fill. No, it's transparent. The back, the color will be gray. And the new guy will be magenta. So it has moved. Ticking wave reaches detector while moving. Except for, let's make the boat bright, the whole boat with it. I mean, it's going to be bright green. Okay. So gray So we need to explain that gray is the position that it was Nicholas Williams, the Planck field. I have no idea what you're talking about. This has nothing to do with Planck. This is just the proof that the speed of a wave is a constant as measured by a moving observer as long as the clock is based on the waves that it is measuring. That's all. It's a very limited proof, but it just so happens to resolve Einstein's postulate. So we can remove Einstein's postulate in exchange for a mechanical universe based on an ether fluid. So ticking wave reaches detector while moving. The gray, we need to have call outs. So a simple call out. So a simple call out is that this gray, so it needs to be over here. So this is the origin, this is the rubber ducky. This is the rubber ducky at the time of oh my god. Mm-hmm. So the rubber ducky at the time of initiating the ticking wave and make it gray. This will be gray. Which gray is it? There's many grays, so it's gray. Right, it's just gray. So is this gray border color? But is it gray? Yeah, I think. Oh no. Wait, what? Gray. Okay. Yes, let's read a message. 1 second, let me check. Wait, I have an important message. Okay. So what we need to check, I need to check something. 1 second. La 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 la. Where can I download message? La 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 la. Let's create a new group. New group. La 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 la. Okay. Next question is so the rubber ducky at the time of initiating the ticking wave. Okay, now I'm hungry. Ticking wave reaches detector while moving. And this is the rubber ducky. Maybe we'll make it 4 pixels. Yeah, it's a much heavier rubber ducky. So this could also be 4 pixels thick. Okay. So that's when it transmitted. This is the arrival. This is the detection. Ticking wave reaches detector while moving. So we can tell that we can see time dilation. This is we can see as what do we call it? Stationary observers. We can see as the stationary observers we can see as the stationary observers so we can see as the stationary observers, we can see the time dilation. We can see the time dilation. Maybe we should make this even a little bigger. Because there's a lot to be said about this photo finish. So this is the detection. This is the time of the detection. This is the detection. This is the detection. Now let's talk about the time dilation. But this should be normal color. Detection. And this is the time dilation. It's basically we can notice time dilation because the wave has to travel. So we as the one second. Mhm. 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 So we as the stationary observers can see time time dilation. The fact that the wave had to go so far. We as the stationary observers can see time dilation. But the rubber ducky cannot. The rubber ducky doesn't know that it's moving. It cannot know that it's moving. As far as the rubber ducky is concerned, it's the same distance over the same ticking. So as far as the rubber ducky is concerned, as far as the rubber ducky is concerned, okay, so this is a very busy image. As far as the rubber ducky is concerned, let's do the calculation that it's distance divided by time as defined by the ticking. So let's copy this. This is going to be 2.4. This is still the ticking wave reaches detector, but this is going to be the calculation. The speed of waves or the velocity of water. Well, all waves, we need to make a note. All waves in this discussion are water surface waves. That's a given. All waves in this discussion are water surface waves. So no other wave is, that's obvious. Okay, so 2.4, so the velocity of waves, 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 the velocity of waves as measured by the moving observer. Maybe we should not call it a rubber ducky because we're going to be intimidating people. Just call it an observer. Moving observer. Moving observer. Shut up, birds. Okay, so before they start building their nest, okay, they ran away. The velocity of waves as measured by the moving observer. Okay, so we need to do the calculation. The velocity. So as far as the moving observer is concerned, it's distance divided by. So we don't need this. We don't need anything. We don't even need the original. We don't care about the original. We can show the original. It doesn't matter. What I want to show is that this is the distance. The distance is, we can call it distance L or D. Uh, so we should maybe put a connector between them. Oops. Mm, no. No, we'll put a square. We'll put a rectangle. Over here. Can we make it like dashed? It's going to be a dashed, It's going to be maybe black. Let me try and write an email. Oh, cannot reply to this email. Okay. Anyway, so this is going to be L. Yeah, I'm going to need to put a connector. So a connector can only go here. So how? So it's not a connector, just a line. A line is a connector. I can't just put it. Can I put it like this? A line like that. Oh, that's going to be such a mess. No, what we're going to do is we're just going to say this distance between the two detectors, that's D, and the time is just a tick. So the velocity measured is going to be the distance. So let's add a call out. This one is going to be all over the place. It's not even a call out, it's just a text box. It's just a text box. So can you convert it into a text box? Change shape. Just a change shape. Just a box. Okay. So the calculation Greek calculation. Oh, Science. Does the rubber ducky think the wave is at the center from their point of view? No, they don't. The rubber ducky cannot see. There's no seeing. The rubber ducky only has a wave detector. This is very important. The rubber ducky, let me add a note. The rubber ducky has no eyes, given the rubber ducky has no eyes. It cannot see anything. It can only detect wave with its wave detectors. That's it. So, to your question, the rubber ducky think that the wave is at the center. Well, the detector is at the center. The detector, it's going to be a point detector. It's basically our eyes. So it's a point detector. From their point of view, that the detector went off. So the tick was registered. The tick was detected. That's all that the rubber ducky knows. If the ducky sees the wave like the stationary people do, then it is not dilation, just time elapsed. Well, there's no seeing, so there's just wave detection. And I could argue that even even the stationary, we know they're stationary, but they don't know they're stationary. So the stationary cannot assume that they're stationary. We can reproduce Einstein's theory of relativity. Maybe we should. So we shouldn't say that, like, we shouldn't say, but we need to show the wave. So, I mean, somebody has to see the wave. hmm Okay. Um, so we know there's time dilation. We as God, but no one else. No one else can. Hmm. What I should do is add. Obviously, there should be an observer in this discussion, which is going to be a second rubber ducky. I mean, the observer needs to be just a second rubber ducky. I will call in when I take a break. So, so right now I'm setting up the discussion. Jesus Christ. Okay. So so this is a theory, right? So I'm talking about the bathtub. So we, as the scientists, we are a bunch. This is going to be the explanation. So we are scientists that we're dealing. Our theory is that there is a rubber ducky, right? Oh, we don't know that there is a rubber ducky. We have a theory that there is a rubber ducky, and all we are a rubber ducky, and we have a theory that there is another rubber ducky running around. All we know about the other rubber ducky is that it is tick tocking. That's all. We just know that it is tick tocking. But even that's not important. For this paper, we don't even need to have no, for this paper, we don't need that. That's for the next paper. There's really a lot to unpack, and I want to make it crystal clear. For this paper, all I want to say is that it doesn't matter what reality is. One second. Let me just check something. hmm So as far as the so this presentation, this paper is just to show that the speed of the waves as measured by any rubber ducky, by any moving observer, is always going to be c. It's just one number. Every rubber ducky, no matter its motion, all rubber duck, even the ones moving beyond the speed of waves, even the ones moving beyond the speed of waves, every rubber ducky will always measure the speed of the waves as c. This is the paper. That's it. This is revolutionary enough. This is enough. This proves that special relativity is just wave mechanics. That's all we need to do. It's enough work. That this is very, very confusing. Everyone is very confused. Until 2 days ago, I was very confused. I didn't know I could prove it. So now that I know, it's very confusing. People don't view relativity as a theory, or as a problem in wave mechanics. They think it's a problem in the real world, in classical Newtonian mechanics. So it's not. If you view it inside classical Newtonian mechanics, then it is paradoxical. But if you just view it in a universe that is waving inside the ether fluid, then special relativity just degenerates into wave mechanics. There's nothing beyond wave mechanics. So the first step in showing that is this step, is to show that Einstein's postulate for the speed of light being constant for all moving observers, that's just what you get if you assume what I'm assuming, the list of assumptions in this paper, namely that we are in a fluid, and the way we measure time is using a clock that uses the very waves whose speed we're measuring. And that basically, that is our reality, because our reality is that because of quantum field theory, we're all waving through the ether. And so everything makes perfect sense. If you assume a fluid ether and we're waving, and quantum field theory, we're all waving through the ether fluid, that's why we all measure the speed of light as a constant. For all moving observers in the universe. All moving observers in the universe measure a constant speed of light, because that is deduced from the assumption of the fluid ether. So that's it, and that's this paper. It's very short, but this is so confusing. This has eluded everyone for 120 years. So I need to do this very, very slowly, very methodically, meticulously. I got to get everything right, and I don't want to, I don't want to be abrasive. Let me just take a message here. So anyway, let's read as I'm waiting for the message to load. Da, 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 da. So if the ducky sees the wave like the stationary people do, then it is not dilation. Very, very beautiful. Very beautiful, beautiful, beautiful. Oh, very beautiful, very beautiful. Okay, and we have a message. Very nice message. Very okay. Let's continue. Um, so if the ducky sees the wave, the ducky doesn't see the wave. The ducky doesn't have eyes. The eyes of the ducky are the detector in the clock. There's two detectors, one for the tick that's at the bottom. We need to specify this. Let me specify this. The names of the detectors, naming convention, naming convention, the tick detector is at the bottom. You can't see that. Let me remove this for a second. So the tick, this is the tick detector. There's two detectors. So there are two detectors, or the rubber ducky has two detectors. One is the tick detector at the bottom, and two no two, and two, the talk detector no be careful, the talk detector is at the top. Extremely confusing, but hopefully this is very confusing because like we're seeing, right, we see the wave, so everybody's like, but we see the wave, so the ducky sees the wave. No, the ducky doesn't. The ducky doesn't have eyes, so let's make that point. Did we see the duck? Did we say the ducky doesn't have eyes? Let's add given the ducky. Yeah, there it is. No eyes. So the ducky has no eye. It's a blind. This is a blind rubber ducky. The rubber ducky is blind. It has no eyes. It cannot see anything. It can only detect waves with its two wave detectors, the tick detector and the talk detector. Amazing. And this could be off the shelf because for paper 2 we'll have two rubber duckies and they would have to be identical. So we need to buy them off the shelf. So somebody can build and sell these rubber duckies. Send them to me to, for evaluation, and I'll give you my recommendation. So everybody, all the laboratories all over the world will buy your rubber ducky with my blessing. You will have my blessing. I will bless the rubber duckies. Rubber ducky, you are here. Blessed art thou, rubber ducky. My God, the water is so terrible. I'm going to kill myself. Nevertheless, all right, let's continue. So, if the ducky sees, right? So, no seeing. So, the rubber ducky, this is the revolution. The rubber ducky always, right? Time is a nice concept, but as scientists, we right, the rubber ducky is a scientist. So let's make a point. This rubber ducky is a scientist. Given this rubber ducky is a scientist, so it doesn't know what time is. It only knows, right? It defines time scientifically as by the measuring apparatus. So given the rubber ducky is, I don't want to say an extreme scientist, but is a meticulous, like, this rubber ducky doesn't know anything except for science. So everything in this rubber ducky's universe is defined scientifically. So the rubber ducky it's a good scientist. Is a good It's a good scientist. So what if he's a good scientist? Therefore, this should be our third paper. What is science? Our definition of science. Okay, therefore, as a good scientist, therefore, the rubber ducky does not know what time is except via time's scientific definition, namely by its measuring apparatus, the measuring apparatus, the metric, the metric is the tick and the tock. There's only a tick and tock. That's the only metric. And the measuring apparatus, as described, the metric, and basically in the metric, there's nothing else. It's metric. So just the measuring apparatus and the metric, the tick and the tock. So what? So that's it. That's a given. The rubber ducky is assigned. The rubber ducky doesn't know what time is. It knows how to measure time. That's it. If it's got to be measurable. Time has a scientific. This is the Popper definition. Popper said it's got to be measurable. Did anybody say this? I don't know. So it's not only, it's a good scientific philosopher. The ducky follows the philosophy of science. Anyway, this is the notion. So this rubber ducky is a scientist. It follows, all it knows about time. It doesn't know anything about time. It just knows, oh, it ticked. Oh, it talked. That's it. That's the only information that the rubber ducky is concerned with. Do you understand? So the rubber ducky is a scientist. Very nice. Very nice. Very nice. So where were we? This one? So the rubber ducky is a scientist. It just measures ticks and talks. And that's why it's always going to measure the same distance, namely between the two detectors. So distance is going to be constant. That's basically the next thing I was gonna add here. The calculation is such that the calculation that rubber ducky is doing is the distance. Well, velocity is equal to distance divided by time. but that's incorrect. It's actually, but well, time is defined itself as the ticking and the talking. Tick, the ticking and talking of the measurement apparatus, aka clock. So time has a scientific definition. It's not just time. What we need the ticking and the talking. That is time. So that's the velocity. Okay. So the distance, that's the span, right? With a ruler, but it's the span between the two detectors. Detectors, it's a constant, which is a constant. The distance is the span between the two detectors, which is a constant. And the time, that's just the ticking. So since the distance is a constant and the ticking, it's always one tick. That's the revolution. It's always either one tick or one tick tock. It doesn't, but it's always the same. That's the revolution. That's the revolution. That's the revolution. That's it. The revolution is the distance is a constant and I don't want to say time, the tick tock king, well, that's a constant, is a constant as well. It's always one tick or one tick tock. Right? The duck is wondering how fast is the wave? Well, this is the distance and this is the time. The rubber ducky is wondering what is the speed of the wave? Answer: distance, constant distance, divided by constant tick tocking. Conclusion: the velocity of the water of the waves is always a constant c, regardless of the rubber ducky's motion. Do you understand? The velocity of the waves, this is the rubber ducky scientific conclusion. The rubber ducky's scientific conclusion is such The velocity of the waves is always a constant c, regardless of the rubber ducky's motion. There you go. There you go. This is revolutionary. I mean, I'm putting it in the most childish form, but this is absolutely revolutionary. This completely annihilates special relativity. Special relativity completely goes away. It is no longer a scientific theory. It is just the way things are based, right? It's just it comes directly out of the ether fluid. If you assume the ether fluid, just as everybody did before Einstein 1905 paper. So if you just assume the universe is filled with a fluid, an ether fluid, like water, then the theory of special relativity emerges. It's not that the theory of relativity replaces the ether, rather, it proves the ether. That should be the conclusion. Conclusion, conclusion. Einstein's theory of special. Special. Shut up, Siri. The theory, Einstein's theory of special relativity proves the existence of a fluid ether that completely fills our universe rather than making the ether obsolete. So Einstein got that wrong too. He thought, Einstein says, my theory therefore dispenses with where he doesn't call it luminiferous ether, he calls it the whatever. And the answer is no, Mr. Einstein, you got that wrong too. You got some stuff right, some stuff wrong, some stuff wrong. This you got wrong. Congratulations. Well, there you go. Anyway, let's continue with your comments. Oh, geez, does the detector of the toy detect the wave coming in from the top, or does the detector detect it at an angle? There's no angle detection. There's no such. No, there's no angle detection. There's no angle detection. You could, you could say that um, when you're moving, can you detect with your eyes an angle? It's a good question. Can we detect motion? Can we detect motion? So when light hits the retina, can you tell where it's coming from? Well, I mean, you have the iris, the aperture of the eye. So you have the aperture, whatever you call it, the whole of the eye. You have to aim it so that it hits the back, so you can tell where it's coming from. So why can we not tell that we're moving? So if I fire a laser, yes, I should see it. I should be able to detect uniform motion. Now that we let's start thinking about the luminiferous ether. So can you detect? Can I fire a laser like just like this? Like, can I be a rubber ducky with a laser, and would I be able to see the change in the angle if I'm moving relative to the ether? I would say yes. I would say yes. You should be able. Notice that, right? The speed is the speed is the speed of light is 300 million meters per second. So you need to take that into account. So if you're moving very fast relative to the ether, yes, you should be able to notice that you're moving relative to the ether. We know that you should be able to do that um, with an interferometer, but you should also be able to do that just with an interferometer. It's just more accurate. You don't need to attain great speeds. You just need either long arms or very high frequency light, like gamma. But you should be able to see the change in the angle if you're moving. I mean, it's a tiny, tiny, tiny change under normal circumstances. But a satellite that is traveling, or a Voyager or Pioneer, one of those fast flying vehicles, um, they should be able to, like, using an eyeball. If they had an eyeball, they would fire a laser at the mirror and look directly at the spot where it should be. Don't look at the dot on the opposite wall. You're not allowed to look at that. If you look, right, if you set your eyeball straight at where, right, if you're stationary, but you never know. I mean, you need to first calibrate the eyeball, like an you need to calibrate a mechanical eyeball. So you fire a laser forward, you hit the wall, you calibrate the eyeball exactly towards. Anyway, look, we can write a paper about that. I don't want to. I don't want this paper. This paper can end up being very, very long because I already started writing the long version. It's a book. It's an encyclopedia. We have to, reinvent all of physics. I'm not doing that now. I'm doing that step by step. Every step I need to be, every step needs to be perfect, and so every step needs to be tiny. If we take big steps, I don't want to take big steps. It's too much work. We want to take very, very small steps. All right. So you're saying, oh geez, does the detector of the toy detect the wave coming in from the top, or does the detector detect it at an angle? It could detect it at an angle. But that's not for today. That's a separate paper. By the way, anyone can take these ideas and you can write the papers. You don't need me to write all the papers. As long as nobody else is writing the papers, I'll keep churning them out. But if you want to write the papers, just as long as you don't plagiarize, because this is all recorded, so don't get caught plagiarizing. Just reference me as the not. I wouldn't even say I'm the original. I mean, I'm just rediscovering what the ancient ones already discovered, that there must be an ether, and Einstein confused everyone, and you know obviously I don't think anyone did anything on purpose. Everyone got confused, so we lost 100 years or 120 years, but it's time to get back on the scientific track. Anyway, oh geez, does yeah, okay. So the next question from Nicholas Williams: atomize the space into Planck units. Stop. Nicholas Williams, stop with the nonsense. We're not doing that. I am doing ether. So everything is based, everything in our lives lives as waves in the ether. That's all. That's all that we're doing. Differential sized Planck unit. Stop. A bunch of them too. Stop. So when people say the ducky sees, nobody means the toy can see. Well, fine. So the ducky only sees waves. It only has wave detectors at as part of the clock. There's nothing else. There's two wave detectors that are basically that make up the clock. It's an analogy to make thinking easier. Fine. Einstein's train is garbage. Einstein invented all these confusing thought experiments. If he just would have explained it's wave mechanics in a fluid called ether, then his theory of relativity would have been superfluous. It would have been just wave mechanics. He would have made many predictions. It still would have been a theory because they still didn't find the ether. So he would have said, okay, we need to keep looking. And with general relativity, there is even more information, and quantum mechanics, even more information. At the end, they would have found the ether. I know today, I believe I know how to find the ether. So the train is nonsense. So Einstein's train is helpful because a person can be on the train doing math and not just a toy. The train is nonsense. You don't need the train. The train only confuses you because the train is a particle, and there are no particles in this universe. You need to treat the train as a wave. If you treat the train as a wave, then special relativity degenerates into wave mechanics. So that's all you need to do. That's what I'm doing. Nicholas, the water molecules need to be able to contract, maybe contact. They are the other observers. No, the water molecules are not observers, they are the ether. The ether is non observer. Science rediscovered, you take words too literally. Are you autistic? I am autistic and you seem like you are too. What the rubber ducky experiences is just helpful words. We don't actually believe toys come alive, lol. Uh, no, I just wanted to. No, I understand what you're saying. I'm just saying that if you meant that the rubber ducky sees only through the wave detectors, then fine, then good, then we agree. I just thought that you thought that the rubber ducky also can see with eyes or something, with optical detectors. There's no optical detectors in this paper. There's just wave detectors. That's what I meant. I'm sorry if I seem like I'm being too literal. I did not mean to be overly literal. I meant to be, forthcoming. Nobody has a clue what you are talking about, Nicholas. Nicholas, you need to reduce to the essentials to get us to your starting point. I think you assume we are in your mind and automatically get it. Yeah, I have no idea. Nicholas is talking about Planck units, and I don't know what those are, so I'm not going to talk about that. Nicholas says the internal clock of the observer, when viewed by a outside observer, decreases as well as light move. What? The internal clock of the observer, when viewed by a outside observer, decreases. Yes, that very good, Nicholas. That is time dilation. Yes. So we're gonna later have two rubber duckies. They're gonna move. One of them will move. The other one is stationary. It doesn't matter. or both will move. We'll play games with two rubber duckies, and we'll show special relativity. We'll show the twin paradox. We'll show everything that we know: length contraction, even relativistic mass, black holes. Slowly, we'll show everything. That's the next step. Right now, there's no time dilation. I don't have an observer. Right now, there is no observer. There's just there's just one rubber ducky in the universe. That's all. So decreases as well as light moving. There's no light in this experiment. There's no light. This experiment is done in complete darkness. That's another given. Give me a second. So given this experiment is done in complete darkness. There are no optical sensors, detectors in this experiment paper Gedanken. In this thought experiment, whatever, paper. Okay. So 6 people are watching. Jesus help us. Nevertheless, nobody has a clue. Good. Nicholas, I think. Nicholas, it's a relative constant. Let's forget about relativity for now. For now, all we want is just to show that the speed of the waves is a constant for all moving observers so long as the clocks they're using are based on the waves, the same waves. The speed of the waves is a constant as long as the time is measured using a clock that is based on the waves. The, the measurement of time, quote unquote, is based on the waves whose velocity is being measured. If that is the case, then the speed of the waves is a constant for all moving observers. Nicholas, mass relative. Forget about mass for now. That's the next paper. Observer relative constant. Okay. Nicholas, the internal clock of the observer, when viewed by outside observer, decreases. Yes, it dilates, as well as light moving with that internal light speed. Let's forget about light for now. There's no reason. Light. Everything you say here about um, the speed of the waves is any wave. Once you can replace wave in the beginning of the paper, it's water waves, but I'll tell them at the end just replace the word water with light, and everything stays the same. So notice. Let me remove this one second. So notice this paper deals with water waves, but the reader can replace water with light and immediately get special relativity. Well, we didn't prove it, but one more thing is that we're not notice that we're not modifying special relativity. Notice notice that this paper is not so much. It's not modifying it too much. The few assumptions that Einstein made are wrong. That this paper is not modifying special relativity. Rather, it is correcting it just a bit. For example, uh, there is there is an absolute frame of reference. It is possible to detect uniform motion in the universe via interferometer, or even by noticing. I'm not gonna get into that now. Maybe okay, or even by noticing a change of direction of light as we, the observers, move at a greater constant speed relative to the ether, something like that. All right. So the internal clock, okay. Therefore, the internal observer detects light speed the same. Have you made any videos or plan on making some, Nicolas? Nicolas, I could try to. I'll give it a try. Very nice. Yeah, I can do that. Good. The duck is a non living toy and a good living scientist at the same time. Hmm. Um. Hmm. Hmm. So, what is a living scientist? How am I different than a rubber ducky, right? I am a rubber ducky. I'm just a more complex rubber ducky, but I'm a rubber ducky. So as a rubber ducky, if I could be a good or bad scientist as a rubber ducky, and I could be a good or bad scientist as a more complex, more evolved rubber ducky. So notice that the first living creatures only noticed vibrations, for example. They could only notice waves, even light waves. They didn't really detect anything more than just vibrations. So they measured if the first amoeba had an internal clock, then the internal clock, if it was, let's say, based on water. So if its internal clock was based on water and it was measuring water as it's moving through water, it would have anyway. So the answer is yes. It is both a non-living and living, because there is no difference between living and non-living. But wait, the difference between clocks, right? I don't know what you mean, Nicholas. Frequency. Yes, the frequency is different. The frequency of the clock changes relative to a stationary observer or another observer. So, a stationary observer will notice the clock ticking slower as the duck moves through the water and speeds up. Your time definition is circular. The ticking and talking were invented clocks because time exists. Good question. To tick tock is to have time. To have time is to tick tock. What is ticking? Yes. But as a good scientist, I wouldn't say it's circular. I would say we can define time scientifically, namely through an apparatus known as a clock. We can define that when it ticks and talks once, that is a second, and that is a measure of time. Time in itself, you could tell stories about it, but at the end of the day, you need, as a good scientist, you need to be able to measure it and have a metric of 1 second, 2 seconds, 10 seconds, and so on. And and your definition needs to be mechanical, and it needs to be reproducible, and all those things. That is science. What is the rate of the constant of tick tocking? No, that is the rate. The tick tocking is the rate, and it's a constant. That's the whole thing. The tick tocking is the rate, and it's always a constant. You have to imagine that the brain of the rubber ducky works only on waves, on water waves. I mean, the conclusion is, right, why do we perceive we're not rubber duckies, right? So you're asking a good question, science rediscovered. Very good question. So this is the main crux of this discussion. The main thing is, so why this should maybe go in the conclusion. So why do we measure? We are not rubber duckies. We are not rubber duckies. So why do we measure the speed of light to be a constant relative to all moving observers? Why is that? The answer is because we are, well, it's based on quantum field theory. The answer is because we are all waving through the ether. This is the conclusion of quantum field theory. Namely, that there are no particles in our universe. There are only waves. And our brains are waving, waving through the ether. And as we move uniformly at different velocities through the ether, our brains wave just like the rubber ducky's clock. Our internal clocks and therefore our consciousness are impacted by our motion, so that our clocks always measure the same tick-tocks, but to a stationary observers have slowed down as per time dilation. This is something that Einstein never explicitly explained. I don't know if he understood it at all. I don't know. I don't know. I don't know. Anyway, that's the answer. This is what this paper comes to explain. This is why we measure, everyone measures the speed of light to be a constant. It's not just our brains and our consciousness, but it's our clocks, our physical clocks. Our internal clocks, therefore, consciousness. This is true for our scientific equipment and our best clocks. Our clocks themselves slow down. Because if you move through the ether, that's what happens. What is the rate of the constant of tick-tocking? Okay, let's make a note of this. Good questions. So notice there is no rate of tick-tocking. Rather, the tick-tocking is the rate. That's it. I mean, this is very important. So what is the rate? Okay, Nicholas. 1 equals time, 1 over r equals k. I don't know what you're talking about, Nicholas. How do you measure time? How much time is between ticks and tocks? That's the wrong question that you're asking. That is the definition. The definition of time is between the ticks and the tocks. That is time. That is the definition of time. It is what takes. Time is what is what is measured by the ticks and the tocks. Should time be measured in change in position of a constant value? No, no, no. You could be stationary. That has nothing to do with it. Of a real or fictional object. No, no, no. Nothing to do with anything. Tick tock just depends on the duck being in water. If the duck is in water, then the clock can tick tock. And to the duck, it's a constant rate of tick tocking. You could say that the rate is a constant. So we could say that the rate is a constant. Instead of saying there is no rate, rather the tick-tocking is the rate. Or one could say that to the duck, the rubber ducky, it appears that the clock is tick tocking at a constant rate, regardless of the rubber ducky's velocity through the water. Okay, that's it. How do you measure time? How much time is between? Should time be measured in change? Okay. Nick, can I call you that? What does time? Yeah, I don't know. Nick, I don't know. One sec. I messed up. Be right back. Okay. Time. An interferometer only needs two arms that are equal length, and it doesn't need. They don't need to be equal length. They just need to be. They don't need to be 90 degrees. I mean, just it's better for them to be equal length and 90 degrees, but all they could be different angles and different lengths. And as you rotate, you'll just get a change in interference. It's a convenience that they should be 90 degrees. That's the most interference that they could cause each other, I think. And the same length, that's, it's a convenience. But they don't have to be precisely anything, not precisely 90 degrees and not precisely the same length. Then the interference pattern of the two lights will constructively interfere. Well, constructively and destructively. So yeah, that's the interferometer. So Michelson and Morley's experiment, we now know, I can do the calculations. I would have predicted a null result. Well, it's not a completely null result. I need to see their data. They might have been able to see something, but I don't know exactly. I mean, they predicted a an ether wind, right? That's nonsensical. So I came to the ether from a theory of gravity, like, and they came to the theory of the ether. Okay, they came to the ether like everybody else from what Michael, not Michelson, Maxwell. One second. So they, so most people came to the ether at that time from Maxwell. So they said, oh, okay, light needs a medium. They didn't think too much about this medium should just be all over the universe. It's basically like a gas. They called it the ether, the luminiferous ether. That suggested it was they felt it would be light, but that doesn't make any sense. In order to get the speed of light, the ether needs to be very dense. It cannot be gaseous. It cannot be ethereal. It needs to be rigid, like like a diamond. So this it's very rigid, very stiff. And they should have, if they thought about it, they would have said, okay, there's no room for, right, there's no room for it. And then they would have said, how do the planets not get stuck in it? How are we moving? And they would have said, oh, that must be gravity, and the ether must be flowing into. They would have come up with GR, with general relativity at that time. So, and then they would have realized, oh, so we should be able to measure the rotation of the Earth. They would have gone to the equator with a more accurate apparatus. But all this, it was not meant to be. It had to wait for me. So here I am. An interferometer, yeah. If the arm changes size because of the ether, then the interference pattern will be destructive. The arm doesn't change size. The arm doesn't change size. This is why I'm doing this thought experiment with the rubber ducky. I'm going to create an interferometer, and in the next papers, we will create an interferometer and we will show that it works and it discovers the absolute motion of the water. So that's doable. So there's no length contraction. You don't need to worry about length contraction because you are moving with the interferometer. So there is no length contraction as far as you're concerned when you're using an interferometer. So you're measuring the interferometer with a constant length. So everything is constant about it except for the angle. And you see the interference, then as long as you see interference as it's rotating, that means you're moving through the medium. So you can go to the North Pole. There you will discover that the ether horizontally is not moving. Then you will check vertically and you'll see that the ether is moving vertically everywhere on the planet. Anyway, let us continue. Nick, what is time progression? What is the unit? I don't know. One sec. Okay. Science rediscovered. Wait, let me go check Science Rediscovered. I want to see your channel. How big? 6 subscribers. Wow. That's pretty good. Here, you have 7. Oh, wrong one. Sorry, 1 second. What is going on here? Why is it switching to my other account? There you go. So I'm following you, Mr. Science Rediscovered. Okay, so you cannot say Einstein's train thought experiment is trash because your rubber ducky is the exact same thought experiment. No, my rubber ducky doesn't exist. It only is a clock. So that's a good point. You're making very good points. So notice that. Wait, can you see my comment? No. Notice that the rubber ducky does not exist. Rather, only its clock exists. The rubber ducky comes to replace Einstein's, I would say, terrible train, not just the train thought experiment, but also train and photon clock, where the photon is it's a ping pong. That is a terrible thought experiment. So everything about his experiment was atrocious. So instead of terrible, let's say atrocious. How do you spell atrocious? Who knows? Does anybody know how to spell atrocious? There we go. Atrocious train and photon clock thought experiments that have sent humanity into this scientific dark ages of the last 100 years that we'll fix in the next papers. That's not for today. I'm not going to talk about what proper science is today. And not in this paper. This paper is purely the corrections for Einstein's theory of special relativity. Very special. Okay. All right. All right. So you cannot say Einstein's train thought experiment is trash because your rubber ducky is the exact same thought experiment. But you forgot that the point was to have two observers. No, this paper is only dealing with the postulate at the beginning of Einstein's paper. He has two postulates. I'm just taking care of the first one. Anyone can read my paper and they'll figure out everything, or they can watch my videos. But I just want to write the shortest possible paper, just to make the tiniest correction to Einstein. I don't want to, like, otherwise it's going to be an encyclopedia. I mean, there's just too much to correct in one paper. So we'll start with this tiny step. Nevertheless, Nicholas Sigmoid. I don't know what you mean, Nicholas. All right. Science we discovered. The train is a particle, then so is the rubber ducky. Good point. You make good points. You make good points. All right. So notice that Einstein's train and photon clock are made out of particles. In my rubber ducky thought experiment, I intend to experiment purely with waves. Thereby converting Einstein's theory of special relativity from a theory about the nature of light to a simple children's toy of wave mechanics. There's nothing. Einstein's theory of relativity has nothing to do with light. It's just wave mechanics. It's not even a theory. It's just wave mechanics. It's just a problem in wave mechanics. There is no, right? We're dispensing. I am hereby dispensing of the theory of special relativity. Well, not in this paper, but in the next paper. I am hereby dispensing with the theory of special relativity. I'm dispensing, replacing it with just wave mechanics. It's just a rubber ducky in a bucket, kitchen sink, or bathtub. Nothing more complex. Yeah. 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 So the train is a particle, then so is the rubber ducky. So hopefully I'm being clear that the rubber ducky represents a wave thought experiment. I'm trying to create a pure wave thought experiment. So ultimately, we are made of waves. So we are waving, and the rubber ducky is supposed to represent that. Notice that we are waves, and the rubber ducky, I don't know if you can see me, and the rubber ducky is designed to represent that. Nicholas, time progression. I don't know. Nicholas, I don't know what you want from my life. Nick, what is a sigmoid? Okay, I'm beginning to become hungry. Sigmoid is the Big Bang, then a period of stability. Okay, I don't know. Nicholas, Big Bang, toroid, science rediscovered. Nick, so between now and 10 minutes from now, the time progression is one Big Bang. Let me think. Nicholas, 1 second. Nicholas, toroid, science. Why is number one given? The speed of the water surface is constant. No, it's not a given. Water speed is not constant. So we, let me see. So it's water. I mean, the speed, the speed of water. Did I say this? The speed of water is a constant or velocity. That's why it's not a good idea to say water. Nowhere should it say water, only at one place. The rubber ducky has a mechanical, there's 6 times it says water. That's not good. That has a mechanical that is based on the surface waves of the water. The speed of the water surface waves is a constant. Well, that's the theory. We, as right, in real life, we don't know, right? We don't know that the speed of water in real life. So, given or in the thought experiment, we're assuming that's why it's given. We are postulating, this is our postulate. We're allowed to have postulates. So, postulate, the speed of the water surface waves is a constant, or the velocity. The velocity of the water surface waves is a constant. Not for all moving observers, that's the conclusion. For any, it's a constant relative to the water. So who's measuring it? If someone imaginary is stationary relative to the water, if an imaginary person is stationary relative to the water, that's a given. If an imaginary person is stationary relative to the water and they measure the velocity of the water, then they will measure it to be a constant. That's what I'm saying. And that's a given. That's a postulate. That's given. From this, we run the experiment. So this is akin to saying that there is an ether and the actual velocity of the ether is a constant, for any given space, right? You could say, well, why didn't we discover the ether? Well, use more accurate devices, you'll see the ether. The ether is, it's not wind, it's gravity. But I don't want to say that now. So I'm just assuming that the universe is filled with this ether. The universe is filled with the ether, with this fluid. The question is, why couldn't we detect it? Okay, because your equipment was shite. Basically, your equipment was shite. So let's notice we need to mention Michelson Morley. Michelson and Morley did not detect the ether because of poor poor prediction and inaccurate and insensitive equipment. That's for the next paper. We're not going to talk about that now. Very nice. Inverse, I don't know. All right. Oh, Nick. Yeah. All right. Oh, yeah. Okay. Nick. Nick, science. The tick-tocking is the rate. No. A rate is a change of one unit over a change of another. How much time or space is between each tick and each tock? So you're saying a rate is a change of one unit over a change of another. I don't know. Like, what would you say is the rate of tick-tocking of a clock? Right, I have a clock on my laptop or on my iPhone. I have a clock. What is the rate of tick-tocking? So you'd say, well, it's 1 second per second. So it's one tick tock per tick tock. I don't know. What, right? What is the rate of ticking of your clock? It's just 1 second per second. It doesn't mean anything. So I think you're wrong. Science. Nicholas, I'm not going to read your comments. It's too complex for me. Nicholas, science. If all clocks measure C to be C, no, clocks don't measure C. Clocks measure T. Clocks are designed to measure time. And distance over time is velocity. And the velocity is a constant C. If all clocks measure C to be C, can't we just shrug and say it is C then? I don't know what you mean by C. C is the speed of the fluid, the speed of the medium. C is the speed of the medium. So I don't understand your question. The clock just measures T. T is a constant. And D is a constant. So D over T is a constant. Therefore, the speed of the medium is a constant. That's true for all moving observers. Nicholas. There's no rate of tick-tocking. The tick-tocking is the rate. This means that there is a rate of tick-tocking. That's like saying there is no species of wolves. Wolves are a species. Look, the tick-tocking is the measurement, is the metric of time. So time is a concept that we define. Part of the definition of time is the test. It's how we test it, how we measure it, and the metric. That is the scientific definition. That is the scientific way. So, so, so time is defined by the rubber ducky through the clock. The clock just happens to be based on the waves. And then the duck, the rubber ducky wants to measure the speed of the wave. Well, it knows the distance, it knows the tick tocking, so it's distance over tick tock. It's always going to be the same distance over the same tick tock, so it's always going to be a constant. I think it's pretty straightforward. I mean, it took me a long time to figure this out. This is years. But once you understand it, I can understand that it's very, very confusing. It confused everyone thus far, I mean, including the brightest minds everywhere. I was listening to lectures yesterday from Professor Shankar from Yale and from Don Lincoln from Fermilab, and they don't understand this. I don't think. I mean, I was listening. The way Shankar presents special relativity and the constancy of the speed of light is this is a magical universe that conspires to hide uniform motion. It's like it's magical. I mean, it's magical thinking. It's not scientific. And these are the greatest minds humanity has to offer. There you go. Nicholas, I'm not going to read because I'm falling asleep and I need to go eat. The convenience of the arm lengths of the interferometer and 90 degrees is to be very precise. No. No, you just need to get an interference. And as you rotate, the interference changes. You Because you always get an interference. You always get some interference. If go watch YouTube videos of interferometers, an interferometer is a standard optical device. You always get an interference, and then when you rotate, or when you modify the length of one arm relative to the other, then you see the interference changing. So as you rotate, you'll see the interference changing, hopefully. But they didn't see it. Michelson and Molly didn't see it because their equipment was just way, way insensitive. Perfect arm lengths and 90 degrees means complete construction destruction interference patterns, which is needed. No, I mean, as you rotate, you hopefully will get one cycle, one wavelength, and even for that, you need, for my calculation, you need 300-meter arm vertically. If you test the vertical flow of ether, that's 10,000 meters per second. The horizontal one is tiny. It's in Ohio, it would have been about 300 meters per second relative to 10,000. And relative to the speed of light, it's one part in a million, but I think you have to square it. So it's even much less. Anyway, it was hopeless. It's 1 million squared, I think, is the ratio. 1 millionth of 1 millionth, or something like that. Maybe just 1 millionth. Maybe I'm wrong. It's about 1 millionth. Their equipment, I don't think, was sensitive enough. They had basically a 1 meter. I noticed that they were using 4 mirrors. So it's 4 meter. So an arm is 4 meter. Yeah, an arm, let's say, is 4 meter because they were using internal reflection to elongate the arm. That's a good start, but 4 meters is still insignificant. So you need, I would say, multiple kilometers to measure any horizontal motion of the ether. That's why they didn't get it. And I'm talking about 1 degree per 90, sorry, one wavelength per 90 degrees. I don't have the calculations in front of me, but they were way, way insensitive relative to what they're looking for. So they didn't have, I don't think they did the calculations for this experiment. I don't know what they had in mind going into this experiment. Convenience, okay. Nick, does the solid ether have gaps? Or is it infinite? No, it's not infinitely dense because that would give you an infinite speed of light. It's very dense. The pressure in the ether is very high, and this pressure, by the way, is caused by the expansion of the universe. This very pressure causes the expansion of the universe. That is lambda. And without it, the universe collapses. So the universe must be expanding. Now I know that Einstein could have, as soon as he came up with GR, this is GR. Ether is GR. Einstein says so. And I mean, ether is GR. And this GR must have a positive pressure everywhere because where you have gravity, that's negative pressure, relative negative pressure, in order to have flow from high pressure to low pressure. So the gravity eats up all the ether, it destroys it. So there's always new ether that's needed to come into the universe. So that is the interglobular space. That's what happens there in dark energy. But that creates a positive pressure, but that expands the universe. And yeah, so that's the explanation. So does the solid so but the dark energy, the pressure that we're feeling, the speed of light is controlled. It's controlled by the rate of dark energy, because that rate creates the pressure. That is the rate that creates the pressure, and this pressure creates the speed of light. The speed of propagation of information in the ether. So I don't know what's going to happen in the future or what happened in the past. I don't know if this pressure was a constant. I didn't think about it enough. That's in a coming up paper. I don't know right now. Okay. Nicholas, I have to skip your question. So if Einstein's train doesn't exist, then it isn't trash. I didn't say it doesn't exist. Einstein had a train, but it doesn't make any sense because he's trying to explain wave mechanics using a train. That doesn't make any sense. He he basically explained that in order for uh, I mean, he explained that everyone, right, light is a wave, but the train is real. That's ridiculous. But our brain, our clocks are waves. So don't confuse us with the train. Just talk about the clocks. Observer A, observer B are rubber duckies, and they have clocks. Yeah, just go use my experiment. My thought experiment is the simplest. You don't need the train, right? At the end of the day, it's the person on the train with his clock, with his apparatus, with his consciousness that is doing the measurement and the experience. And those, Einstein agrees, those are waves. Because he says the speed of light is a constant for all moving observers. That means those observers must be waving through the ether. That is what he's saying. That's an important point. So when Einstein says, when Einstein postulates that the speed of light is I think maybe I wrote it already, is constant for all moving observers. What he is actually saying is that all the observers are, and their brains are waving through the ether. That is what he was saying. That is what he was postulating. Whether, how do you spell weather? That's not how you spell weather. Whether he explicitly said it or not. That is immaterial. His postulate assumes it or implicitizes it, says that his postulate assumes it implicitly. So I don't care if he was aware of it. I don't care. It is implied. Oh, implied. Implied it implicitly. Yeah, this is very deep. This is this has confused. Atrocious. Hello. Wow. How is everything? So atrocious. Nicholas. Okay, so if Einstein's train doesn't exist, then it isn't trash. Atrocious. That's how you spell it. And how did I spell it? Well, my Google Doc spelled it for me. What if I don't see a difference between your experiment and Einstein's? I don't care if the duck is real, the clock's aspect is the same as Einstein. No, Einstein is not scientific. Good point. You're asking the best questions. You cannot believe Einstein, right? You said, what if I don't see the difference? You cannot not see the difference. Einstein is not scientific. Einstein's thought experiment or theory of special relativity is not scientific. It is magical thinking. It postulates a constant speed of light for all moving observers for no apparent reason. It's completely reasonless. It is completely reasonless. As such, it is unscientific. As such, it is unscientific as science must be reasonable. Science is reason. Science is reason. It's other things, but at least it is reason. As such, it is unscientific. We must reject Einstein's theory of special relativity as a scientific theory. It is not a scientific theory. It is a magical theory. It is not a scientific theory. It is a magical. Shut up, Siri. It is a magical theory. It's about magic. It postulates that this universe is magical. It postulates that our universe is magical. Notice, yeah. Notice that most, I would say that most of the conclusions of special relativity are still relevant, but some are not, i.e., we can detect uniform motion using an interferometer. Oh, there you go. What if I don't see a difference between your experiment and Einstein? That's I cannot help you then. If you don't see the difference between science and unscience, well, then you need to study the philosophy of science. You need to come up with a philosophy of science. That means you don't have a philosophy of science. Your science and your magic are the same. You don't have you don't have an understanding of science. Then you don't understand what science is. You conflate science with magic. I don't care if the duck is real, the clock aspect is the same as Einstein. No, no. Einstein did not use a duck. Einstein went into light and did not explain why the speed of light is constant for all moving observers. And no one has ever dealt with this. I am the first person to prove it, to explain it. So you cannot tell me that there is no difference. It's the difference between postulating a nonsensical idea that you would never have thought of, that the speed of light is a constant. Everyone who teaches Shankar, I was watching his lecture yesterday when he was teaching this, he took maybe an hour or half an hour to tell us how counterintuitive the constant speed of light postulate is. And his explanation was, well, it's because we assume that the universe conspires to hide our uniform motion from us and other such utter unscientific nonsense. So Einstein destroyed science. I'm not going to say that in the paper because I don't want to look this whatever well, we have gone through. Well, maybe I'll just make a note. We've gone through. Hopefully, this is the end of this dark age. Hopefully, wait. Let me just put it right next to it. Okay. Hopefully, the dark, the scientific dark ages that hopefully the scientific dark age that that science has collapsed into this past 120 years. Wait, did somebody just text me something? So, hopefully, the scientific dark age that science has collapsed into this past 120 years, basically since 1905. 19 it started in 1905 basically, and it's going now, we're in 2024, so it's almost 120 years. So hopefully the scientific dark age that science has collapsed into this past 120 years has finally come to an end. Hey, what's up? What's up, Andrew? What's up? Can you hear me, Andrew? Can you hear me, Andrew? Oh, 1 second. Let me. Yeah, yeah. 1 second. One, two, three. Oh,
Yo,
yeah, yeah. What's up?
you're recording?
Yeah, I'm
Uh,
actually recording, and there's questions, and I'm writing the paper on the
wow,
postulate. Yeah, yeah. Here, let me give you the link. 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 Where's the link? Here is the link.
Hi, daddy slave.
What? Who says that?
No one.
Anyway, here is the link. Anyway, let
All
me
right.
finish. And I'll talk to you. I'll take a break. I'll talk to you. Away from keyboard. Okay. Okay. So, Okay, so we're writing maybe the final sentence of the paper. So hopefully, the scientific has finally come to an end. Yes. Hopefully. Mhm, 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 mhm. The postulate is the water speed is constant. The speed of the medium. The postulate is, well, it's not his postulate. I proved that we don't need the postulate. His postulate is about the speed of light. But when light does that, but when light does that, it is because all clocks measure c. But no, clocks don't measure c. C is the speed, it's distance over ticking. But water speeds literally change. We're talking about the speed of water waves. So it's a postulate you disprove by splashing the water. There's no splashing. There's only water waves. Do you really mean what you said? Do you really not understand my proof so much? Oh my god. I hope you're joking. Okay, guys, let's bring it to an end. It's 3 hours, and I need to eat, and I need to go out. Nick, and the TikTok is the change of motion over time. No, the TikTok is just the TikTok. The TikTok, the the TikTok has nothing to do with motion. I don't know what you mean by motion. Don't know what you mean by motion. Nevertheless, all right, let's continue. So, change of swing over change in time. Well, there's no swing, there's water waves. Science, what is this constant of t? I don't understand your question. Uh, Science, yes, you always get interference, hence the arm length and angle maximize that effect, which is precision. Okay. Arm length doesn't matter because the interference pattern doesn't change with length. Well, if if you change it in real time, so an interferometer allows you to change an arm's length with a micrometer. It has a special dial that you can change the length of the arm and see the interference change and measure the lambda. That's what they use interferometers in labs to calibrate, to measure lambda. Ba, 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 ba. And one more. Oh my God, still many. Okay, guys, let's bring it to an end. I'll continue later. Sorry, you say you proved something about light or wave or whatever. Can we talk through your proof so I can better understand what I'm? Well, not now because now I need to go eat and drink and get out, and I'll come back later. Alligator. All right, everyone. That's about it. Thank you very much for participating. Thank you, Nick. Thank you, Science Rediscovered. Good questions. Um, Let me give you a link to the paper. I don't mind if you have a link to the paper. Share general only people with access. No, this is anyone with the link can comment. Copy link. I would even give everyone a chance to write the paper. Um, Maybe we should do that. Anyone can, but then anyone can destroy the paper. So if you want, make a copy of the paper. Here is a copy. Make a copy and submit copies. You can submit copies, and I'll try and read your paper and review it, and maybe I'll use parts of yours with permission. But if you submit, you're giving me permission to use it. So because I'm explaining it, so you can do the hard work. I might mention your name as a reference, not as a writer. So here's the link to the paper. You can read it, look at it, enjoy it. I'll also put it in the Discord. There is a science forum. So in the Discord science forum, I'll create a new post. Here's the link. I can't post. Enter message. Paper. Post. It's not clickable. Can you? I just copied the link. Let's try this again. Where's the paper? Share. Copy link. Okay. What I want to do is. Oh, there's the link. So if I click it, yeah, you can see it. It's good. Oh, there's already somebody. Oh, that's probably me. I'm assuming. I don't know. Okay. Read the paper. Give me comments. You can write, anyone can write comments on the paper. It's open for commenting. Also, you have the Discord. You can comment on the Discord. Um, and that's it. All right, everybody. Let's take a break. I don't know. It's now already very late. But I might eat and come back and continue the very hard, laborious work. All right, everyone. Thank you again. See you later. Bye bye.